This is the second video lecture on Hurricane Exercise Part 3, looking at damage and death from hurricanes, tropical cyclones. So up to this point we have taken our nominal value of damages from hurricanes and we converted them into real dollars, for real 2017 dollars, and we can do that. We see it here that we basically took the original nominal value and divided it by the conversion factor that we're taking from the data conversion factors sheet. So now that we have those values adjusted to today's dollars, that means that we can do comparisons over time, which is going to help us in our later analysis. But for right now, we want to compute some basic summary statistics of our data to get a sense of what's going on. So we're going to put those statistics at the bottom, and since we're going to do that, I'm going to freeze the top row again so that I don't lose my place. So I'm going to go to the View menu, and I'm going to choose the Freeze Panes. I'm just going to choose to freeze the top row for the moment. So now when I scroll down, I don't lose track of what the column headings are. Now, you may see occasionally, and I brought this up before in class, if you see these pound signs or these hashtag signs, that just means that the data can't fit in the columns. You can adjust that by just widening the column a little bit, and then it'll reveal the data. It's not an error or anything. Okay, so we're going to compute some basic summary stats. So we'll do the typical ones that we do, and I'm going to put the labels for them in the ACE column since we're not going to use any data there. That'll be easier. So we're going to do the max. Oops, can't type max. I really can't type x. Okay, min, range, the mean, median, standard deviation, and then a new one that we haven't looked at before, the coefficient of variation. So let me widen this column just a bit. There we go. So I want to compute those statistics for each of these things. So you know how to do these formulas, so we can do that pretty quickly. Recall that there is no formula for range, so we just take the max and subtract. We do the standard deviation, we're doing the sample. And then the coefficient of variation is a new statistic we haven't done before. And essentially, it's a measure of the variability in the data, but it's dimensionless, which means that you can compare data sets that have very different types of data, very different ranges of data. So I'll compute it right now, but you'll see what it means in a second. So it's a very simple one. We take the standard deviation and we divide it by the mean of the data. Okay, and so we'll come back to this in a second. We want the same statistics for our real dollars. We're going to leave the nominal alone since we're not terribly interested in that. So once I have the formulas, I can just copy them over and I can paste them into the column over here, and the formulas work the same way. And just to keep it clear, I'll format those as dollars as well so that we can see what we're dealing with here. Okay, so real quickly, the coefficient of variation is a way of comparing the level of variability in the data, so that if you have data with very different ranges, consider, for example, here we have our data runs from 0 to 8,000, where over here it runs from 0 to 369,000. And so if you were trying to say, for example, whether there's more variability in depths compared to damages, it would be hard to tell by looking at just the standard deviation, because the absolute values of those numbers are so different. However, the coefficient of variation takes into account or it normalizes it by the type of data you're working with. And so what you end up with is a new number that lets you to more directly compare. And so what it tells us here is that the level of variability in the two sets of data is really similar. So they're actually both somewhat equally variable. And so that tells us that the data kind of are behaving in a very similar way, which is kind of foreshadowing what we're going to see later. Now, what we're interested in here at the moment is to understand how representative these summary statistics are of our data. And we've gone over this quite a number of times in class. So you know what most of the statistics mean, right? In particular, we paid a lot of attention previously to the mean or the average, right? And the significance of a mean or an average statistic is it's supposed to tell us what the typical data is, or the typical value is for the data. The expectation is if the data is behaving quote unquote normally, we expect that most data values in the data set are kind of somewhere in the vicinity of the mean, with the standard deviation telling us like roughly how far and above and below that value most values are. If the data, though, is not normally distributed, where it's not following like a typical bell curve, then that may not be the case. The mean or the average may not be representative of most of the data. So in this case, for example, if we're looking at deaths, right, the average annual number of deaths, or the mean, is 174 deaths, right, per year. So the question is that typical? Is it typical that in a given year there's 174 or close to that, deaths from hurricanes? Well, the way that we can judge that right off the bat is to look at the median. The median is always, by definition, in the middle of the data. And so if the data set is normally distributed, then we expect the mean and the median to be, if not exactly the same, really close to one another. And in this case, we see that they're not. They're pretty far apart. And the same thing can be said for the damages, right? So the fact that the mean and the median are really far apart tells us right off the bat that this is probably not normally distributed data. So it also means then that the average or mean is not really representative of the data, and so we have to be really cautious on how we interpret that. There's other clues, of course, to that. For example, the standard deviation is huge compared to the mean. So if you imagine this kind of range around the mean, the standard deviation, is 800. So if you subtract that from 174, you're going to end up with a really large negative number. So clearly there's something funny going on with the data. It's not normally distributed. So we just kind of put that in the back of our minds because we want to keep track of what it is that we're dealing with. Now, one of the questions we have is what to expect from this data. So the means, as we've just determined, aren't terribly representative of the data. And if we were trying to understand the threat of hurricanes, we might want to calculate what's called an expected value. So the expected number of deaths or the expected damages in a given year. And the expected value is a little different than the mean or the average. It takes into account the probability of an event. And so we've been doing with this throughout the class so far, and specifically it takes into account the recurrence interval and the exceedance probability of hurricanes. So just like with floods, we can use recurrence intervals and exceedance probabilities as a way of describing or characterizing an event, right? Like a disaster of this sort. So in order to calculate that, which is what we need in order to figure out the expected number of deaths or damages, we need to calculate the recurrence interval. So we've done this before, so we'll go through the process of calculating, first of all, the number of years in which there was at least one event. So I'll say we're going to calculate the years in which there was at least one, or how many years were there was at least one. And that will allow us to calculate the recurrence interval, which will in turn allow us to calculate the annual exceedance probability. So, for example, if we want to know how many years in our data set was there at least one named storm, right? So we use the COUNTIF function in that case to count the number of years in our range here that were greater than 0, essentially. So here that means 1 or higher, right? So I put the criteria here in quotes right there and close off the parentheses. And so that gives me a count of how many years there was at least one of these events. And so you can see there's 120, which means that in every year there's been at least one named storm. The recurrence interval takes into account the number of years or the number of years of data divided by the number of years in which an event happened. So this is essentially the number of years is going to be the count of years of data that we have. So this is going to be in the first column, the number of years that we have, A2 to A121. So we take that number and we divide it by the years in which there was at least one event, right? And so that number right there, which just shouldn't be 100%, it should actually be 1. So here we're going to turn it back into a numeric value. So I'm reformatting it so it's proper. Okay, so as you might recall, or you should recall, a recurrence interval of 1 means that these events happen. There's on average 1 year between these events. So every year, essentially, you get one of these events, or at least one of them. To turn that into an exceedance probability, we take the value 1 and we divide it by the recurrence interval. Okay, and so that value we do want to be in a percentage. So I'll go back and format that properly here. So that means this is the probability that you will have an event, at least one, this year, right? So it's a 100% probability. Not surprising, because again, you see these storms happen every year and more than once normally. We can then, once we've set this formula up, we can calculate it by moving it over to the remaining columns, and we can see slight differences between the years. But interestingly, the recurrence intervals aren't terribly different between years. So even with major hurricanes, right, hurricanes of a category 3 or higher, we see that there's quite a lot of years, most years, out of 120 years of data that we have, 105 of them had at least one major hurricane. So the recurrence interval is relatively low, meaning there's a short time period on average between these events. And then conversely, inversely, the exceedance probability means that we have a very high probability of this kind of event happening. So if we were trying to understand the expected events, right? So here, for example, we said what we're interested in saying is the expected average annual damages, right? What that means is we're going to take the average that we calculated previously for damages, right, with the mean right there, and we're going to multiply it by the exceedance probability. So if we were looking at named storms, we'd multiply it by this number right there. And so what we're doing basically is we're taking the average annual, but we're multiplying it by the probability of the event. And so that should modify the number slightly, although in this case it's 100%, so it doesn't change anything. It's the exact same number as the average, right? But let's say, for example, that instead of doing the exceedance probability for all cyclones, what if instead we used the AEP for major hurricanes, right, which is slightly lower. It's not 100%. So in that case, if we calculate it that way, you see that it's a slightly different number. So this number varies slightly from that number because the exceedance probability modifies it just a little bit. But for the purposes of your exercise, pay attention to which one you're being asked about, right? When you're not being asked for the one about major hurricanes, you're being asked about the one for named storms, I believe. So we can do the same thing for expected annual deaths. If I can spell. Yep, there we go. All right, and it works the same way. We basically take the mean number of deaths and we multiply it by the exceedance probability of the type of event that we're talking about. So we can see in this case it's no different than the actual mean because, again, these probabilities are so high. But you can imagine in other cases, whether we're talking about floods or other kinds of events that were much less common, the expected numbers would be lower than the averages that we work with.